Interference figures are quite unlike normal microscope images. They represent the integrated effect of light travelling in many different directions through a grain. Interference figures are useful for determining optic sign and whether the mineral is uniaxial, one optic axis, or biaxial with two optic axes. We'll start with figures in which the optic axis is vertical. Here are the main steps to getting an interference figure. This sequence illustrates the procedure for finding an interference figure. Firstly, we will be scanning round the slide, looking for the suitable grain, crossing the polars for each field of view and also using plane polarized light, rotating the stage between cross polars to pick our suitable low interference colour grain. When we think we've found one, we'll go to medium power, carefully rotating the turret by the rim, refocus, this is most important, centre the grain close to the crosswire intersection, rotate between cross polars to check that it is a low interference colour grain, check in plane polarised light that it is the right mineral, and now we're ready to go to high power. So providing it was focused, we can swing the high power around, refocus this time with the fine focus, not the coarse focus, and then check the centering of the stage of the microscope. Our grain must remain near the crosswire intersection. And now we're ready to get a figure. We firstly rotate the auxiliary condenser in the case of the grey Reichert, into position. We then make sure that the diaphragm is fully open, which it is. We make sure the polars are crossed, and we swing in the Bertrand lens and focus the Bertrand lens to get the clearest image of our interference figure. Several variables can affect the appearance of an interference figure. Here the swing-in condenser is out, and here it's in. Here the diaphragm is being closed and opened again, and it must be fully opened. This is the effect of a lower magnification objective, and here's the effect of the high power objective again. The retardation, the product of birefringence and thickness, determines the number of isochromes. The following figures show the effect of decreasing retardation. Here the maximum interference colour, third order red, maximum interference colour, second order blue, and maximum interference colour, first order grey to white. Most centred uniaxial interference figures are like this one and lack isochromes.